So it is open book and open notes, and the scope is from everything after the double precision floating point numbers and all the way to compiling code. Okay, so the programming part using TTP is a part of it. So that means the lab on Tuesday is actually really relevant to this particular exam. Okay, so for those of you who actually spent the effort, spent the time, on Tuesday to try to figure out the answer to especially the last two questions, you were already studying for the exam. Okay, so in other words, we should have been studying for the exam all along. Okay, this is not something that people should be studying for like 2 days and expect the results. Okay, just like in the previous exam, it is open book and open notes. So that means you can bring anything that is printed on traditional paper, okay, not e-paper, but traditional paper. Um, and as long as it is on paper, you can bring it with you. But there's no sharing during the exam, okay? So if you want to work together to come up with the same material to bring to the exam, that's fine. But once we start the exam, there will be no sharing of the material. So are we okay with that? Okay, so basically the same rules, okay, common sense stuff. No, there should be no big unexpected stuff here. All right, so I'm just going to go straight into the content of the exam unless there are questions, so please do not hesitate to ask questions. All right, so here's the first question. It is basically I describe a circuit to you, and then you have to give me the NC node connectivity / PD propagation delay diagram or in a chart. So the description of the circuit is on the first page, and then the actual circuit is on the second page. So this is the actual circuit, and for the most part, you do not need to refer to the first page because it is already partially filled in this case. You just have to fill in the parts that are missing in this particular table. So the way this is formatted, or this was formatted last semester, is either a whole column is filled out already, or it is not filled out already. So that means if you see a column with some stuff that is already filled in, you don't have to fill that column. Get that column is already filled in, which may or may not be the format that you will receive when you get your version of this kind of exam question. Okay? Are we still doing okay so far with this? All right. So and there's no need to do any type of explanation with this particular question. All you have to do is to fill in the missing transitions, changing of the values, and that's all you need to do. So we'll go ahead and start with, I'm not sure how, can you guys see the, yes?
Is this the SR latch, or what is this particular circuit?
I will not talk. I will not give you guys that clue ahead of time. So all you have to do is to actually go through the whole process. Okay. So I do not talk about what type of a circuit it is, but okay. If you look at okay, I know for people in the back it's a little harder to see it, but if you look at the labeling, this is input pin. This is AND. This is NOR. This is out pin, this is not, this is AND again, this is NOR. So in other words, we know the type of the components. And then we also know the ports too. So for input pin, this is just the port. This is for input pin, this is just the port. This is in 0 of an AND gate. This is in 1 of an AND gate. This is out of an AND gate, and so on. And then the connectivity is established by the numbers on the top. So this is node 1, and you can see that this is node 1, this is node 1, this is also node 1, this is node 0, this is node 0, this is node 2, and this is also node 2, and so on. So let me just pause here and see if there are any questions about how, when you combine all of these description on the top part of each column, you should already have an understanding of what the circuit is. So are we good with that? Okay. All right. So now we can go ahead and try to answer some of these questions. Okay. So we're trying to fill in some of these steps. So how do we get started? Okay. You basically just have to, yes, go ahead.
Well, maybe start with which pins are electrically connected.
That's implied by the node numbers. So yeah.
That's where I would start.
Yes, okay, very good. So as in the process of answering the question, you do need to be aware of all of those things that I just talked about, okay? Node connectivity, which ports are connected to which other ports, what kind of component we are talking about. In this specific case, we have AND gate, NOR gate, and NOR gate, NOR, okay? So we'll go ahead and get started here. So at this point, this is given. When you see two pins that are both faced, they are given to you already. There's no need to explain why they are zeros and ones in this particular case. It is the same setup as your NCPD lab. Okay, so if you go back to the NCPD lab, it is basically the same process, even though the circuit is different. So do we have any questions about that? Okay, all right, so let's go ahead. So this is node 1, so that means everything on node 1 should be updated to a 0. This is also node 1, it is updated to 0. This is also node 1, it is updated to 0. So we are good there. This is on node 0, and we can see that this is node 0. It is also updated to a 1. Oh, I take it back. Everything on node 1 should be updated to 0, okay, which is the case. Everything on node 0 should be updated to 1. So this is updated to 1, this is updated to 1, this is updated to 1. So this row is all done. Okay? Are we good so far? Alright. So the next row is PD, which means that we are looking at things where at least one of the input pins has changed in the previous NC row, and then we want to figure out whether the output is going to change or not. So now we have to focus on all the input pins. This is an input pin, so that means potentially the output pin of the same device may be changed as a result. So now we have to look at the kind of device it is. It's an AND gate. So if one of the input pins of an AND gate is a 0, do we know for sure what the output pins should be?
Yes.
Yes, and it should be a 0. So that means we have to identify that, put a 0 here, because all the columns are assumed unknown to begin with. So from unknown to a 0 is a transition, so that's why we have to write a 0 here. All right, so we look at another input pin that just got changed, which is this one here. This is a NOT gate, and the output pin is already documented here in the provided table to be a 0. So we don't have to worry about the entire column because it's already filled in. This is also a 1, which is transition from a unknown, and this is a 0, this is a 1, and these are the two only input pins of this particular AND gate. So if we know the input pins of an AND gate are 0 and 1, do we know the output of that AND gate? And it's going to be another 0 over here. Okay, yes?
This is being recorded.
I believe so. I can double check.
I want to make sure before we go into the...
Yep, it is recorded. Now, that being said, as much as I appreciate the reminder to record my lectures, not all of your classes are going to be recorded, which means you still need to kind of take notes as a backup. Okay, I would just say that. Just in case my computer does not catch on fire, having the hard drive completely destroyed before I had a chance to upload it. That can potentially happen.
We'll forensically recover all your data.
Or just, it's a SSD, it might be a little bit hard to recover the data if it is burned.
We try.
Good try. All right, so the next row, so this row is now all done. The next row is an ANSI, which is node connectivity. So we look at the PD row, and then we say, oh, this is node 3, it just got changed to a 0. So that means we have to locate all the other node 3 ports and change all of those to 0s as well. So this is the originating one, and the only other one is over here, and we have to go to the ANSI row to change that one also to a 0. And then I believe there are only 2 that connects to node 3, and that seems to be correct. So this is node 4. now we have to look for all the node 4 and also change those to zeros. And here's another node 4. I believe this is the only other node 4 port. So now we should be done with the NC row. So the rest is just kind of like this, okay? It's not super exciting, okay? But it is something that you kind of have to show me that you know how to work with this table. So we are back to another PD, which means that we are looking at potential changes of output ports because of changes to the input port. So now we can see that this is freshly changed, and we now ask, do we know the output of this port here? Unfortunately, we do not, because this is a NOR gate. If one port of a NOR gate is a 0 and the other one is unknown, we still cannot determine what is the output of the NOR gate. So that means we cannot put anything here. This one here is also changed recently, and this is also belonging to a NOR gate, which also means we still cannot determine the output here because in1 is still unknown for this NOR gate. So we are done with this PD row. This particular PD row is empty, which means we are now at a steady state. Very good. And as a result of that, the next row, the next NC row starts with a 0. That is bold-faced because it is a change of the input. So now we look at this 0, and we already know that the NC row for both input pins are handled correctly. Okay, so we can just kind of move forward to the next PD row. So the next PD row is looking at things that have input pins changed. This is one change, but the output is already here. This entire row is already done, so we are not too concerned about that. Now this one is also changed as a result of this 0 here, and it is in one of an AND gate. So this AND gate is now having 0 as one input, 0 as the other input, and as a result, the output is going to change to, well, it's not going to change because it is still a 0. So we're good here. And let's see. So I think this PD, this NC is done. That's from before. I believe this PD is also done. So when this PD is also done, then we look at port 2, node 2, which got an update, and then we have to make sure this is reflected in the next NC row, so you can see 2 is also updated here. But we'll double check and make sure that there are only 2 ports corresponding to node 2. So I'm just going to scan the top here. This is a 2. This is a 2. There are only 2 ports that connect to node 2. So this is completed for the NC. And then the next one is another PD. Okay. So this PD only has to look at this one change here. And this change is from an AND gate. So you can see how this is a 1, but this port is still a 0. So this AND gate, this particular AND gate, still has at least one of the input ports being a 0, which means the output continues to be the 0 that we see here. So there's no change. So that means this PD is also done, and it is also completely empty because we have arrived at another steady state. Which also explains why the next row starts with a input pin that is bold-faced, because bold-faced means this is an output. This is a change initiated from outside of the circuit. It is not the result of the circuit itself. All right, so we know the first NC row is going to be done in this case. Now we have to look at the next PD row. So this is automatically done, so we're not concerned about that. But we do have to take a look at this one. So with this one, this is input pin 0, which is still a 0. So that means the output is still going to be a 0. And so not putting anything here is correct because we only write down something when there is a transition and there's a change. So this is all done. And there are no other input pins, so we are all done here. This 0 in return is node 2. So node 2 is propagated to this 0 over here. So that concludes this node connectivity row, and that is correct. And the next PD row is all empty, but you might want to double check and make sure that that makes sense. So we're going to double check. So from the perspective of this AND gate here, this is a 0, this is also a 0, the output continues to be a 0, so that is actually, we just verify that it should be an empty row, so we are all good here. This is another input pin change, okay, so that's all good. And this part here, okay, this portion here is all empty. So, and the next row that has a bold phase input pin change is right here. So that means most of the work is going to be from here all the way down to here. Okay, so we'll work on this gradually. So the nice thing about something like this is you can still get partial credit if you kind of mess up a little bit here, because I'm just looking at where the changes should happen, whether it is happening in the correct way or not. Okay, and when people start to guess randomly and try to put down like zeros and ones at random spots, I would notice that pattern too, and that would basically be a zero. Okay, because a 0 out of 4 means the answer does not reflect any understanding of what needs to be done. So if somebody is just starting to write down some zeros and ones, even if some of those zeros and ones so happen to be the correct answer, the overall score is still going to be a 0 because I can see that, oh, that person is just really trying to guess, right? All right, so we are now moving on to the most difficult part of this entire question, okay? So we will take a look at this one. Okay, this one is covered. So you might want to bring a ruler with you, okay? Because to line up the rows and the columns, having a ruler can be very helpful. So I suggest that people will bring that. If you have colored pencils or highlighters, you can consider bringing that. But depending on the number of nodes here, you may not have enough colors to make it really visible. So I personally would just kind of stick with the numbers, but if you like to use color coding and whatnot, you can try to do that. But I cannot say that it is going to be effective in the exam because of the number of nodes that are involved. All right, so this particular AND gate still has a 0, 0 and 1 is a 0, so it is maintaining a 0. So we know there's no transition here. And then for this one, we know something has to happen because there are so many rows with nothing until we get to rows that has something. So we know this one kind of have to do something. So this is a 1, this is a 1, and the output of the same AND gate has to transition from a 0 to a 1. So there's a 1 going to be here. So you go like, oh, so that means the entire PD row only has 1, 1. That is correct. And so you can all down here. So the NC is going to take this one, transition to a 1. This belongs to node 4. So we locate everything on node 4. This is the only other thing on node 4. So we have to kind of be careful where to put the 1 or the transition of the 1. We have to put it here. So this is also where when if you have a ruler, it can really help because it makes things easier to line up. So there's a 1 here, and that's all we need to do for this NC. And now we are down to another PD. There's only 1 pin that got changed in the previous NC row. So now we have to take a look at this one. And this one is not. Oh, this one is going to make a change because this one belongs to one of the input pins of a NOR gate. So now the question is, if at least one input pin of a NOR gate is a 1, what kind of guaranteed output are we getting out of the NOR gate? 0. It's guaranteed to be a 0. Very good. Okay, so this means in the next PD row, that is going to be a 0. And then for the first time, node 6 is getting a transition. So now we have to locate all the ports that belong to node 6. I believe there's only 1, which is this one over here. So now that one also has to be changed to a 0. And now we're done with this NC row. And then for the next PD row, it is just because of this 0 here. Because now we know for sure both input pins of this NOR gate are 0. 0 NOR 0 is a 1, so we put a 1 here, but the table already has that provided, but we just want to double check and verify that as well. So this one is belonging to node 5. Now we have to locate everything on node 5. Is node 5 is node 5, and both of those particular node 5 columns are already updated correctly by the table itself. And then we have another PD, and this PD we are just double checking because we already know that it really should be empty, but it doesn't hurt to double check. So now we take a look at this one here. It is belonging to a NOR gate, and the other pin is a 0. Oh, wait, take it back. Let me double So we have 1, 1, you're getting a 0, okay, that is still correct, no change, no transition. This one is, that's an output pin, so there's nothing to do for us, okay, because it's not a device that is going to change. All right, so that means if this PD mode being completely empty is verified. We kind of know that it should be empty already, we just need to double check. Yes?
We always assume that what you have in there is correct, right? It's like if I was doing something and it conflicted with what's already on the table, that means off, right?
With this particular example, you just gave me an idea. Oh God, yes, that would be the correct response.
No more questions.
No further questions, Johan. No, I'm not going to do that.
That would be funny though.
No, it wouldn't.
He does it in the last question.
The last question is, the last question, that's a very classic way for me to ask questions about coding, especially in this class. So when we get to that question, okay, if you guys have not read the question, the last question, we'll get to that. But if you have read the last question, it's not as difficult as you think it is. You just have to be careful and really understand the activity. All right, so getting back to this one, we're almost done. The next transition from outside is a 0 here, so that's propagating into these two. This one is already done, we're not too concerned. And this one is an AND gate, and this AND gate has to be turned into a 0, the output of the AND gate, because if at least one input of the AND gate is a 0, the output of the AND gate has to be a 0. So now we're done with this PD, and then we have another NC. So at this point, it is a little bit difficult for us to kind of see the transition because I have to maintain everything from above in order to answer the question down below. So I would do one thing that you should not be doing, okay, just because I'm presenting this on the screen and there are some limitations regarding the what I can do. So what I will do, okay, which is not something that you should do, is to copy everything from above, so just so that we have continuity from to the everything below. So I'm going to copy the current state of every single port. That's interesting. Because even with this glove, it registered my touch. Oh. Okay. So if I don't touch it at all, it does register. That's funny because this is supposed to stop the touch registering, and it still did the job. I'm going to return it, and someone's going to buy it used from Amazon.
They're going to return it. Cycle starts all over again.
All right, so I'm just copying the current state from every single port, and having a ruler will be very handy right now. I can still do this without.
You should just disable scrolling when you get the pen tools to it.
Yeah, it's not because of that. It's because the bottom row is also touched here. And if I touch it first and then I use the pen, it becomes the eraser tool. So it's not because of scrolling here. The scrolling part is not the issue. The 0 here, and this one is also 0. This is a 0. This is a 1. Okay, there we go. So now I can scroll to the next page, and now you understand why I have to do that, because otherwise I lose track of all the states of the earlier, well, not all, but most of the states of the ports. So now with this NC, oh, I just lost track of the NC. I lost track of which one I just put in the previous row. All right, that is an interesting problem, but we can solve that problem, not a problem. All right, so this 0 becomes this 1, we got that. That 0 becomes this 0. That's the only transition. So this is the one that we have to NC, that we have to propagate through the node connectivity. So, see, not a problem, not a big problem, little problem. And I lost track of all the TBD too. So I think we might actually have to. So the other solution to this problem is going to be a little bit of a problem for you guys because I can turn this into portrait mode and I can see everything now. But it does become a little bit smaller from your end, and I can't zoom in any further because that's how the web page is. That's how it works. So if I do a control, I cannot zoom in any further here. So how do you want me to do it? Do you want me to kind of keep flip flop in between, or do you want to keep it in portrait mode and then it is visible from here? Portrait mode is okay. All right. Well, the whole thing is still getting recorded, and I think the recorder has enough resolution, and you also have a PDF version of the same test.
Yeah.
So I think this probably will work out fine. All right. So now I have to take off my glasses because I have to look much closer. I kind of have to smell the tower. Yeah. Okay. So this 0 is propagated to everything on node 4, and this is the only other node 4. And not having a ruler is okay. That's kind of a little bit issue here. Okay, put a 0 here. That concludes the particular NC. And then this is a PD, which means this 0 to a NOR gate is going to change the output of the NOR gate to a 1. And then that concludes this PD. And then this one, which belongs to node 6, is going to propagate to all the other node 6, which is the only one that's up here. So now we follow that all the way down here. This is now a 1. And because at least one pin of the NOR gate is a 1, the output becomes a 0. That explains this PD. And now the NC is to take node 5, which is now a 0, and also connect it to all the other node 5. So the other two node 5, one is here, one is here, which explains these two zeros over here. So now we just have, we are almost there, okay? 3 more rows. And the test does not always indicate that you have to use up all the rows. So I will provide you enough rows, but not always just enough, which means you might have additional rows that do not need to be filled in. But so that's why we have to double check. All right. So this 0 is belonging to a NOR gate, and this is also a 0 that belongs to the same NOR gate. So the output is going to change to a 1. So we do have one transition here. This 0 is an output pin, so it's not going to trigger any changes. So now we're done with this PD. This one, in return, has to propagate to everything else on node 6. So the other node 6 is this one here. So now we go down to here. This now turns into a 1. Oh, it does not turn into a 1 because it is already, wait.
It's already a one.
Oh, that means that this one should not be here either.
I think you might have, I don't know, I have to appear and it looks a little different, but I feel like I did it right.
Okay.
I feel like, because on the row you filled in, right under it, I think because it's the pin number 4 that changes, and I think you updated.
Okay. So let me check this part. So this is wrong, this is wrong. Is that correct?
The one above it.
The one about the PD?
The PD, the one, the NC, I think, because the pin number 4 got updated to a 0, because that's the H out, and then that's pin number 4, and then the NOR N1 for A, N1A changes to 0.
So are we referring to this row here, this N0?
No, the one, like 3 rows of one.
Oh, this one?
One of them.
This one?
Yeah. The 0.
So I put the 0 on the wrong spot.
Is that 4A? I can
This
see it.
is, yeah, this is 4, and this is also 4. I want to understand what you were.
No, you're good. The one.
Well, I actually have the key too, so we can take a look at the key, afterwards. Okay. So that means that this 0 does not trigger any actual change, so there's no PD entry here, because this is a 0, 0. No, this does trigger a change.
The one maybe? The one on the PD row under the one also.
Can you count from the bottom? Which row?
It's the 8th row from the bottom.
8th row? So 1, 2, 3, 4, 5, 6, 7, 8. This one?
Oh, no, the one under it, sorry.
Say again?
The one under it, sorry.
This one?
Yeah.
You mean this?
The one.
Let me take a look.
Yeah, the 1 and 0.
This is a NOR gate which has 1 and 0, so that means the output has to be a 0. You're correct. Okay, good. So now we can see where needs 2 hands and then 2 of these. Okay. Alright, so we can fix this one. So there's no transition here. If there's no transition there, there has to be a transition somewhere because we are not done with the transition states yet.
Oh, we have a 1 and a 1. And that updates the F out.
We have a 1 and a 1.
We have one, F in 0 is a 1. Just got updated in the row above it, right? Yeah, because
Which column?
the 7th column on the bottom.
1, 2, 3, 4.
Oh, no, column 3, sorry, column 3. Not
Column 3. So this one got, oh, okay, I see. So this is an input into an AND, so we now have 1, 1, so the output becomes a 1. This becomes a 1. Okay,
That's
thank you.
Sorry.
That's all right. Yep, so that means this one here. Okay, so I'll just work out the rest. I'll delete that one too, because I think that's from earlier. All right, so if this is a 1 and it belongs to node 3, so we're going to have to update all the node 3s to 1s. This is the only other node 3. Okay, so we got this one updated to a 1. And this one explains why this becomes a 0, so we're all good. This 0 is connected to these 2 nodes, and that's the same node, they belong to the same node. So these 2 become zeros. So now we have 0, nor 0, which should become a 1 over here. This is a 0 to output pin, so there's nothing else affected. So this one is then using the node connectivity to connect to the only other node 6 pin, which is this one here. So that one gets updated to a 1 over here. And that should conclude the whole thing because 1 more 1 is still a 0, so the PD row over here is empty. So that should conclude the whole thing. Well, thank you for reminding me that I made a mistake on that. All right.
Copying the row is to do it.
Yep, that's right. Yep, go ahead.
Will this circuit oscillate?
No, because we ended up at a steady state.
Well, I tried to make it logicent, and it says there's an oscillate.
That might have to do with how you start the initial state. But it should not oscillate because I tested the circuit as well in Logisim, and it did not oscillate when I tested it. It is actually one of the many implementations of one of the devices, memory devices that we have talked about. It's just one of them. All right. So, do we have any questions about this answer, or what you need to know to answer this question, or what you need to bring with you to answer this question? This one, I would say, for the most part, the only thing you need to bring to answer this question is your brain. Or possibly some of the truth tables, but NOR gate truth table is pretty easy.
Can we borrow someone's?
Hmm?
Can we borrow someone's?
You can do that prior to the exam, not during the exam. You mean the brain or the nodes? You cannot borrow somebody else's brain. You can borrow nodes, but not in the exam. All right. All right, so that's that for this one. All right, so we can now move on to question number 2. All right, so question number 2, I'm going to turn it back into landscape mode, at least for the time being. So the question says you are given the following node/tunnel values. So to answer this question, what do you think you're going to need?
The CPU diagram.
Yes, you're going to need the CPU diagram. You might as well also bring along the ALU and also the register diagram. Okay, just in case I forget to include that in the exam. Okay, so in this particular exam, I did include all the diagrams. So if you kind of fast forward to the next page, it is actually on a physical page. So the idea is I put it on a different physical page so that you can kind of remove the paperclip so that you can kind of look at the diagram on one side and then try to answer the question on the other side. Okay. But just in case I forget to include this diagram, you might want to just print it out and include it with you, bring it with you. And the other thing that's nice to bring your own is you can use color coding, okay? Which means all the things that are important, all the things that you want to start with, you can color code it so it becomes easier for you to locate, oh, where's the program counter? It's right here. Okay, where's the register bank? Right here. So I think it really helps to bring your own, okay, just in case that I forget to include it in the question itself. All right. So question number 2, part 1. Identify what components as destinations is or are updated. Okay. So what can update? RAM can update. You can change the content of the location of RAM. Registers can update. And that's about it. Okay. So that means the answer to part 1 is going to be a list of registers and or the RAM component. Okay. There should be nothing else. So now the question is, how do you identify from this part here, what is going to be updated? What do you think?
Look at the enable pins.
Right. Look at the enable pins, but first of all, start with, what can update? What are my registers? So you have the program counter as a register. You have the instruction register as a register. You have the 4 registers inside the register bank. They update because our IEN is enabled. Okay, so you kind of have to keep in mind, how do we update one of the 4 registers in the register bank? It is by RIEN being 1. Okay, and then RAM itself can also be updated. If RAM is selected and RAM load is a 0, then we are right into RAM. So RAM can also update. So those are the only things that really will update. So now we just kind of go through this and go like RAM select is a 1, but RAM load is also a 1, so RAM is not updated. RIEN is a 1, so that means one of the 4 registers in the register bank is going to update. But which one? RISEL is going to tell us which one is going to update. In this case, it is register 1. So components that can update, the answer should include a list of the names of the components and also include an explanation. So now we can say register may be because, okay, because. We can always use abbreviation here. In this case, it's because RIEN is 1 and RISEL is a 0. Okay, so that's 1. And then we move on and talk and see if anything else is going to update. The program counter is also going to be updated because PCEN is a 1. So now we say PC because PCEN is a 1. Okay? And that concludes the part 1 of this particular question. And I gave you like a sample output here, or sample answer, which has the right format and obviously the wrong actual answer. Part 2, for 50%, use RTL to describe how each component in the previous part is updated. Next to each RTL, list all the bits and only those from ROM.D that are involved in the configuration of the update. Use tunnel names whenever they are available. An example of this format, is this is updated, becomes instruction register becomes instruction register plus one because of blah, blah, blah. Now, this is totally bogus, okay? That is not a valid answer for anything. I'm just showing you what the format should look like, for this answer. All right, so that means, in this case, we have to say, register A is something because of some connectivity. We also need to say PC equals to something because of some connectivity, okay? So this is where we kind of have to reference back to the diagram, of the processor, because I cannot remember, how the registers and the multiplexers are all configured. I have to look it up, okay? So let's go ahead and look it up. We know register A is, okay, I probably want to find a slightly better way to do this, or do you guys want to stay with this? Because, I can, okay, so I'm going to start with loading up the, without my glasses, it's a little bit harder to see, to navigate. Give me a second here. All right. There we go. Nope, that's not it. There we go. All right. So I am bringing this into, oh, because this is in full screen mode, it doesn't want to share the screen. There we go. Okay, it doesn't want to share, but all right, I need to find a way to do this. Give me a second. First, we get this back, and then move this to another monitor. Nope, it doesn't want to do that. There we go. We should have it on this side now. There we go. And this zoom out just a little bit too much. So a lot of this stuff, that I'm doing right now, you don't have to worry about, because if you have the diagram already on paper, it's easier to just to cross-reference that. All right. So for the rest of this, I'm just going to read from the exam here, because it's otherwise it looks even more confusing, because I have to switch back and forth between the exam question and also this diagram. All right, so we know register A is getting updated. So that means we have to track down, what is wired, how this wire is connected. So this means that we have to first look at RI lux in this case. In the question, RI lux is a 0. So that means, okay, let me use the mouse pointer. So we have to track down input 1 of the multiplexer. So there we go. So we have to track this down, and it goes all the way to RAM. We already know RAM in this case is selected, and it's also in read mode. So that means register A is getting something that is coming from RAM. Okay, so in the answer, okay, so yeah, I do have to kind of switch between the two, like so. So in this case, we know that register A is going to get the dereference of something because it's reading from RAM. Whenever you're reading from RAM, it is dereferencing something. There are two things that can act as a pointer. It is either a register from the register bank or the program counter itself. Now, we don't know which one yet. Okay, so that's what we need to track down. So so in this case, we also have to record in the answer that RI mux being 0 is a reason. Okay, this is part of what we need to track down. So if we switch back to here, then the next question is, how do we know what is driving the A port? So now we have to track down the A port. The A port is, before we get to the A port, the two inputs of this multiplexer has to go through this multiplexer. And in the question, ADDR mux is a 1, kind of like this one. So I have to write down in the answer. I'll switch back to that when it is the right time to do it. So in the question, ADD or mux or address mux is also a 1. So that means input 1 of the multiplexer is set to the output. So now we have to follow the input 1 of this multiplexer, which is coming out of the program counter. So this is how we know that we are dereferencing the program counter. So in the answer, let me switch back to the answer here. So in the answer, I just added that register A is the dereference of the program counter because that RI mux is a 0, and we also know that it is because ADDR mux is a 1. Is that okay? So one side, the RTL itself describes what is happening, and then the other one, quoting certain configurations of the tunnel is explaining why that is happening. Is that okay? All right. And now we have to track down how the program counter is getting updated. So in order to figure out how the program counter is updated, we have to follow the D port of the program counter, which is this one here. It is coming out of the multiplexer, and the multiplexer is determined by PC mux. So this is where the trick, that there's a really important thing to remember, is PC mux does not come out from the ROM, but PC mux is. So now we have to look at PC mux, which has a value of 6 in the question. So with a 6 as a going into with PC mux being a 6, that means input 6, which is a 0, is why PC mux is a 0. So now we have to in the answer. I will show the answer in just a second here. So we have to specify PC mux being 6 is important because that explains why PC mux is a 0. Okay? So if PC mux is a 0, then we follow the input 0. It's coming out of the adder. But whether we're adding 1 or not also depends on your ADDR mux, because that is ORed with PC Inc. And ADDR mux in the question, I believe, is a 1 already. So ADDR mux being a 1 is also part of the reason that the program counter is hitting program counter plus 1. So let me go back to switch back to the documented answer right there. So this is the answer to part 2. We identify that we not only are we updating register A is given the value that the program counter is pointing to. Not only are we updating the program counter, but we also know that the program counter is incrementing in this case, and the explanation is down here. Yes?
Would writing A gets the dereference of PC++ also clear?
Yes, but then you have to be careful because PC++ should be parenthesized.
Yeah, with the dereference on it.
Yep, that will also work. All right, are we good so far? All right. And then the next page, the third part of the question is asking, according to the previous part, which is part 2, which instruction is the best match? In other words, of all the instructions that is in the opcode table, which one is best matching the RTL that we saw in the previous part, the answer to the previous part? So in this case, it is the LDI instruction, okay? Because we are loading PC asterisk PC++ into register A. So we know it's an LDI A with something, but we don't know what that something is because that something depends on whatever is the program counter pointed to before the increment, and the question does not tell us about the memory content. So all you can do is to use a question mark or dot 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 or something along that line. Yes?
In the picture you have, it says 8B. It says 8B in the value of the PC on the one on the test.
Yeah, but you still don't know the content at that location.
On the RAM, yeah.
Yeah. So you don't know what is the value of that's the second operand.
RAM and then like that location.
You just leave it like this. That'll be fine. All right. And the last one is part 4 is to ask you about the opcode. So now you have to use the opcode table to manually assemble the instruction. So we can do The opcode table is also something that you should probably bring with you. Okay, so print it out, bring with you, so that you can do this part. And this time we know it's a LDI instruction. So LDI is, where's LDI? I'm blind. Right here. Okay, this is LDI. So this is LDI. So that means, and the question specifically is asked, what is the binary opcode? So that we specify 0, 1, 1, 0, 1, 1, and then register A corresponds to 0, 0. So we have 0, 0 over here. And let me switch back to the tablet so that you can see what the answer should look like. So that would be the answer. And this part does not require an explanation because it really is just looking at the table, figuring out what the bit pattern should look like. All right, so that's question number 2. Do we have any questions about question number 2? Yes?
What is the ROM D in the first part? Like, what is ROM.D from 0?
It's the D part of ROM.
Is there a reason for them, or do we end up?
Oh, you mean the bracket 0 here? You mean this one?
Like that information being given to us.
Because it is part of the output. So I just decided, I'll give you everything that the D part is output. But otherwise, it's not important in this case. Neither are these two. Okay, these two are also not useful because if one specifies that we are not resetting the microcode pointer, and then the other one I cannot remember. I think it's choosing the it's for the multiplexer that feeds into the microcode, but it has to be one in this case. Yeah. So these three are for this question is not really particularly useful. It cannot be used to explain things in the question. All right. So I do not want to have to explain what RTL is in the exam. Okay, so if you don't, you should know it by now, but if you do not, you might need to review your notes just to make sure that you know what RTL stands for. All right, so do we have any other questions about number 2? Okay, so you might want to jot down what you need to bring with you to answer a question of this nature. Okay, and obviously there are many other ways to ask you about this kind of stuff. Okay, because I can easily reverse the whole thing, give you the actual instruction, and ask you, how the pins or how the ports should be configured. Okay, so there are quite a few ways for me to, ask, to assess whether you understand how the processor itself works or not. All right. So shall we move on to the third question? Yeah. All right. So let's move on to the third question. And here's the third question. So question number 3 is based on the C code that is commented out below, you are provided with an erroneous implementation. Note that the TPP ASM implementation, which is erroneous, may include optimized use of registers as well as flags without changing the meaning and structure of the C code. Your job is to identify the bugs, explain what they are, what the bugs are, and fix them. Fix the bugs. And then to identification, what is supposed to be done and what is actually being done. Okay, so you have to kind of explain, oh, this is not what it is supposed to be doing, and this is what it's supposed to be doing. Explain why the expected work is not done. It can be an error or an omission, which means sometimes I can give you the wrong instruction or the wrong operand of the right instruction. Other times, the instruction can be missing entirely. Or I can give you an extra instruction that not only has nothing to do with what we need to do, but it will also mess up what we're supposed to do. So you have to kind of identify those issues, and then change the code to make it work as expected, basically fixing the bug. Yes?
Can we technically just convert that into TT-PASM and then basically just check the matches?
You can do that, but you cannot. If you make changes that are not necessary, those will be counted against you. Do you understand what I mean?
Yeah.
So you can go ahead and implement this code on your own, okay? But if suggest changes to the existing code that is not necessary, those will be counted against you. So it does, so that's the challenge. Okay, you're supposed to understand my implementation and locate the problems with my implementation, not just to re-implement the whole thing, in your own way. Yep.
So the C code itself also has a bug, right?
No, the C code is fine.
The C code is
The C code may not have the C code is just a C code. It may be completely meaningless, may not do anything useful. What we are really looking for is the consistency between the assembly code and the C code. But do not assume the C code is wrong. The C code is the reference.
Whether there's a infinite loop or not doesn't really matter, right?
That is correct. But typically, I would not give you something like that. I'll give you something that is at least have some meaning to it, and so that it's at least the whole exercise has some meaning to it. All right. So this one is also kind of difficult to do by using a split screen. So instead of doing a split screen, I think this one I can do a little bit better because I can just use a normal text editor to show you the code. So let me do just that. And before I do that, I need to, I'm looking at two pairs of glasses on the table. I have to pick up the correct one. There we go. All right, so we are going to go to the text editor and take a look at that. Okay, so we can do an nvim. Okay, let me bump up the font size a little bit and then maximize. And I need to look at the question number. Okay, this is in it's from the previous semester, so it's a 4.9. And the file is x2q3 dash 000 dot txt. There we go. Cool. All right. So I'm going to do a split screen here so that we can look at the C code on the top, and then we can look at the assembly code at the bottom. Oops. Switch to here first. Okay, there we go. So that's the C code. I'm skipping all that. And I'm going to turn off syntax highlighting or spell off. Oh. How do I make it so that it doesn't do any? Well, okay. It's trying to look at this as a text file, and it doesn't. Okay. Give me a second here. I'm going to change this to TTP ASM and copy that to a different folder. CP, all of this to x2.ttpasm. There we go. Okay. All right. So this is the C code, and here we have the assembly code. So I do have an unfair advantage that the editor is syntax highlighting. Everything that is not valid is already like short of the blaring sound effect. It is pretty, yeah.
So those two have to be LDI?
Yes, they both have to be LDIs. Okay, so you basically just have to. In this case, there's not really a whole lot to explain. You can just kind of go like change LD to LDI. Okay, and same over here, change LD to LDI. All right. So that takes care of B equals to 7, D equals to 1, A equals to 0.
38 has to be compared on a 4.
Yes. So okay. So let me explain how to analyze loops and control structures like that, because the label names are very specific. Okay. So unless you guys request that I do not give you meaningful label names like this, instead, we just want label L1, L2, L3. I usually prefer to give you guys at least some clue as to what the labels are and what is the meaning of the label. So while zero begin is the beginning of a while loop, and obviously while zero end is marking the end of a while loop. So that is actually helpful to you because this way you kind of go like, okay, let's check the control structure here. If this is a while loop, there has to be a JMP 0 all the way back to while begin, and we can see that that is missing. So that means, right away, okay, knowing that we have a while loop and there's a missing unconditional branch at the end of the while loop, I can already tell that there's supposed to be a JMPI here to while 0 to begin. Okay, and then I can comment and say this was missing, and we need this to have a loop. Okay, well, that's enough explanation. All right. So this is how I do things. Okay, I analyze the code in the structured way. I don't go just line by line. So now that we have fixed this problem, we go back to the beginning of the loop, and then we ask, okay, so how do we get out of the loop? So now we go back to the beginning of the loop. We look at the C code. Okay, the C code says as long as register D is not 0, stay in the loop, which means as soon as D becomes 0, we exit the loop. So now we look at the assembly code and ask, okay, are we doing the right thing? So between and or, one of them is already hijacked. Or is the one that is hijacked, which means and is the one that is not hijacked. So that means in this case, it really should be and. Okay, so I even give you a comment here of checking for 0. So we need to change this or to an and. Okay, this needs to be changed to an and. Change or to and because or is hijacked. Okay.
Can we use a comparison
The thing is, you cannot. So in this case, if you use a compare, you have to load 0 into another register. So if you implement it correctly, yes, you can do it this way. But the intention is for you to notice that or DD is supposed to be and DD. All right, so this is the correct conditional branch because when D becomes 0, we should exit the loop. So now we go to C equals D. C equals D is implemented by CPR. That is correct. We are adding B to D. Add BD is going to do the right thing. So that's all correct. And now we have if C is greater than D. So now we have to compare the two. But the question is, how do we
DC?
Huh?
Compare DC.
Compare DC. Well,
we're checking that D is less than C.
Okay, so now we have to look at the polarity of the condition. So let me go back to the C code and scroll down a little bit on the C code first. Okay. All right, so here's the C code, and this is the assembly code. Let me just scroll up so everything is in the context, in the correct context. There we go. So we want the then statement to be implementing A. So this means implementing A on line 46 is the then statement. So how do we get to the then statement? We get to the then statement when C is greater than D. So now the question is this code going to do that? And if not, how do we fix it? Compare CD is subtracting D from C, which will change or update some of the flags. So now if they equal, we want to go to the else case. Okay, that sounds correct to me. If it is less than, we're also going to the else case, which sounds reasonable to me as well. So this code, there's nothing wrong with lines 43, 44, and 45. Is that okay?
Yeah.
Yes, go ahead.
Are we looking at them as assigned or unassigned?
So now the question is, okay, that's a good question. Are they signed or unsigned? So that depends on how the C code is. Yeah, I think the C code makes it signed, right? Yeah, so it is signed. So that means that we do have to fix one of these. So this is supposed to be JLI instead of JCI. So JLI because C and D are signed. There we go. Thank you. Good job spotting that. And then incrementing C is fine. Okay, let me scroll back down to the context where we were at. Okay, there we go. So the else is corresponding to this part here. We just want to subtract 1 from A, but there's no such thing as subtract A1. We can use decrement. So we basically say decrement A. So we explain, I just pressed the wrong key. Go back to this point, okay. Cannot subtract a immediate in the sub instruction. There we go. And this is the end of the if statement. It's the label for the end. Then you go like, wait, if there's a label called while 0 end is 0, I don't see any branches to that because the then branch, at the end of the then branch, we're supposed to have an unconditional branch to the end of the conditional statement. So that means that right after the increment A, you need to have an unconditional branch to the label that marks the end of the conditional statement. So that's also missing. So now I'm going to add it back. JMPI to while 0 underscore and if 0. This was missing, causing the then statement to flow into the else statement, and that's why this JMPI instruction is necessary. We do okay so far? All right. So I have a little question for all of you. When did we learn all this stuff? What was the module? Compiling. Yeah. The module that talks about compiling. That's when we learned all this stuff. All right. Okay. So getting back to the C code, I believe that is it. Okay. There's nothing else we need to do because we have fixed all the problems in this case. Okay. And we still have 5 minutes left. Yes.
Just a quick question. On the actual exam, do you want us to write down the comments, the expressions like comments?
No, you can use any notation because you're going to do on paper. So that means you can use whatever notation that is clear to me, what change you're making and why you're making that change. So you can draw arrows and make boxes and whatnot.
Okay.
Yep. All right.
As long as it makes sense.
Say again?
As long as it makes sense.
As long as it makes sense to me.
Yeah.
Yes.
Yeah.
Because it may make sense to you. If it does not make sense to me, then you still cannot get the points. we do have a lab today. Okay, so I did prepare a lab for you guys today, and I think all of you can already guess what topic is on because it's all about the stack operation. We talked about the stack on Tuesday, and we are gonna have a lab about it today. Cool. All right, so I'm gonna make it visible. And on top of that, to make things a little bit more interesting, this one you only have 3 attempts. I think it doesn't impact a lot of people, but I'm noticing that some people just go like 6, 7, 10 attempts and go like, that may not be the intention of the lab. So you only have 3 attempts on this one. Yes. The access key is LIFO, LIFO, lowercase. All that means is you just have to go slower, okay? Just kind of make sure that you try to understand the material before you ask any questions. All right. I'll see you all at the lab.